Okay, whoops. This. All right. So I left off talking about the meaning, okay, the meaning behind these equations. We are looking at the contribution of the weight causing it to change position. And we're relating that to how the momentum is kind of changing along with the velocity, okay? Your mv is changing along with the velocity. So each step of positional change is equated to a velocity change and scaled by these, the mv and the mg, okay? So that's kind of what we're talking about here. Instead of trying to relate velocity changes to time changes, what we're trying to do is relate velocity changes to positional changes. That's the goal of our analysis here. So what then does it mean to integrate this? To integrate it means to add up all of those little individual changes over a macroscopic change, a net change. So if we were to graph this on the left-hand side, what we're saying is, as you have a change in y, and you graph it versus the weight, the force of gravity, which is mg, what does this graph look like? How does your weight, what is your weight as a function of vertical position? What do you guys think? It's constant. Your mass doesn't depend on where you're at. And g, as long as you're close to the surface of the Earth, right? For the most part, you know, there's a limit to this model, but this model is for when you're close to the surface of the Earth, it's flat. It's flat. So we're saying that if you take a little slice of positional change, okay, and you look at the area under this graph, the height of this area is mg. And to integrate is to take over a large amount of space. That's your integral. That's your integral. You're adding it up over the whole space. You're adding up a bunch of these little boxes, which is essentially a Riemann sum. Okay, Riemann sum is adding up a bunch of these little boxes. Okay, your Riemann sum is eventually taking all these little boxes, and again, you take the limit as the width of those boxes becomes close to zero, or essentially zero, right? The limit when it gets to zero, how small, when you get the smallest infinitesimally sized boxes, you add it all up. Okay, that's what the left side represents. Although I guess you can argue it's negative, right? It's the negative. So that's the left-hand side. What does the right-hand side look like? Put that over here. I want to leave a little space because I'm going to write some more. So on the right-hand side, what will be on my x-axis that represents this integral? What will be on the x-axis to represent this integral? V. Right? If we're taking slices of y, and that was the y here, now we're taking slices of v. In other words, we're looking at how this is related to this variable. Okay, when you integrate, your dv or your dy at the end of your integral always tells you what your slices are, and that is kind of like your independent variable under consideration for that particular integral. Okay, what you're adding up against. You're adding up all these little slices of this, or you're adding up little slices of this, and so on and so forth. Okay, so on this axis you have mv. Okay, so how does mv depend on v? What kind of pattern will that be? This we've called P, right? Or momentum. How does momentum depend on velocity? Yeah.
It's just like linear, but it has a y-intercept.
Sure. Yeah. It can be linear with some y-intercept. You can start with some initial momentum, and you can start with some initial velocity, and mv is linear with a slope of m, right? So, this area is what we're interested in now. This is the area that we're interested in. Okay? And this area represents this integral. Okay? So notice that what we're saying here is by doing some mathematical analysis, you can take Newton's second law and then say there is a relationship, an equation, an equality between this area of the weight over a position change to the momentum over a velocity change. They're related. So that means that I should be able to figure out how my speed changes based on where something is, not how much time something has fallen, which is what we're trying to get at. Okay. So we've done this before. We did this last time. This ended up being this, like a delta 1/2 mv squared. Right? And sometimes in calculus, we'll write it like this. Right? We are integrating from some initial velocity to some final velocity. It doesn't really necessarily have to start at 0, right? I mean, we can be looking at this area or whatever. It can be any range. Okay, and we said that this is our kinetic energy. This is K. Okay, so we've done the right-hand side. We did that last time. Let's look at the left-hand side. So the difference between what we're doing now and what we did last time is last time we said for a generic force, right? I have the notes here still from last time. We said that you just have some whatever force, right? This time we're looking at a specific force. The right-hand side is still the same, but now we're looking at, instead of just some F net, we're looking very specifically at gravity. We're analyzing potential energy for gravity, or not potential energy, work from gravity. So if mg is a constant, just like with derivatives, constants you can pull out. So you can say that negative mg integral of dy is equal to this delta k. I'm simplifying a little bit. So what is the antiderivative of a constant? It's just the variable, right? So if I said the derivative of what gives you just a number, you would say like the derivative of 3y or 3x gives you 3, the derivative of 5x gives you 5, so you want the other way around. So then the derivative of what gives you mg, it's mgy. Okay. So I'm going to write this kind of a variety of different ways. So we can write it like this. Negative of mgy final minus mgy initial. This term, the mgy, this expression, I'm going to call this U little g, U subscript g. This is the gravitational potential energy. Yeah. Okay, that is gravitational potential energy. So then essentially what we have here is a negative change in gravitational potential energy. which is then therefore equal to the change in kinetic energy. So you have to lose gravitational potential energy in order to gain kinetic energy. Or if you gain gravitational potential energy, you must lose kinetic energy. Let's think about how that looks. If I raise an object up, okay, if I have positive positional change, right, then I must get that energy from somewhere. So if I take a pen, an object, and I throw it upward, right, I throw it upward, it starts with more velocity, starts with kinetic energy. It loses kinetic energy because it comes to a stop, but it has gained height. It has gained gravitational potential energy. It has gained mgy by losing kinetic energy. When it comes back down, it loses mgy, it loses gravitational potential energy, but regains kinetic energy. So this is kind of a mathematical representation of this conservation of energy, or that your energy is transforming from gravitational to kinetic. Okay, so we can write it like this. Another way we can write it is if I write it out, I can rearrange this part to say, if I distribute my negative, in other words, I can say mgy initial minus mgy final is equal to 1/2 mv final squared minus 1/2 mv initial squared. Sometimes it can get kind of confusing about your finals and initials and why it's sometimes initial minus finals, sometimes it's final minus initial. When you look at the change in any property, it is always final minus initial. The only reason why this is initial minus final is because there was a negative there. When you distribute the negative, it'll switch the subtraction. Okay. So what I can do from here is I'm going to put all my initial stuff on one side and all my final stuff on the other side. So I'm going to add this over to the left and I'm going to add this over to the right. So you get mgy initial plus 1/2 mv squared initial. Whoops. Equals to mgy final plus 1/2 mv final squared. And so essentially you have a initial gravitational potential energy plus an initial kinetic energy must equal to a final gravitational potential energy plus a final kinetic energy. Sorry, that should be a G. Right? So initial energy, final energy. The energy you start with should equal the energy you end with, therefore conservation of energy. Now this is only for a free-falling object, right? There's no other forces involved. And so what we can demonstrate from here is that the energy involved in gravity is conservative. You can get it back. Okay, if gravity is the only thing involved, it can transform from kinetic to gravitational and back and forth without any losses. Kind of like momentum. As we'll see, not all forces act like that. Any questions so far about any of these calculations? Is it hard to read? All right. So what is the advantage of this? Let me give you an example where everything you've learned up until now would not help you solve this kind of problem. Let's say you have a ball on a swing, a pendulum, and you lift it up, and it starts here. The initial velocity is 0, and it has a certain amount of mass, and you let it go, and so it swings. And at this point, it's moving. I asked you, how fast will it be moving when it got there? That's a really hard question to answer with everything that we've done so far, because everything we've done so far has been generally uniform circular motion, or we tell you I guess what the forces are, or what the acceleration is, or something along those lines. They give you a lot of information. But if you actually try and do the free body diagram of this, it's kind of hard to know how all your accelerations will play out. It's really hard to use Newton's second law on this because gravity is always pulling straight down, which means that the angle that it makes is sometimes in the radial direction, sometimes in the tangential direction. At this bottom part, it's purely radial and not tangential, and everywhere in between, it keeps changing. Your tension is at these different angles, your gravity is at different angles. So it's really hard to do just sum of the forces, because when you sum your forces are changing, which means your accelerations are changing, which means that your kinematic equations that you've learned so far for constant acceleration, you can't use them because your accelerations are changing. So it makes it very difficult. But what we can do with this is say that if it started at a certain height, then it must have had a certain amount of gravitational potential energy. And when it goes down to the bottom, that gravitational potential energy must turn into kinetic energy. And so from there, we can actually figure out how fast it's going based on where it started and where it ended without caring about anything of what happened in between. That's really one of the most useful things about energy is as long as it's conserved, we only care about what happened before and after. Is that hard to see? Yeah. Okay, we only have to care about what happened before and after. So we can write it out like this. We'll write it like this. mgy initial plus 1/2 mv squared initial equals mgy final plus 1/2 mv final squared. Okay, so my initial mgy, that's like mgh. Whoops, yeah. My initial 1/2 mv squared, that's 0. If it starts at rest, right? Starts at rest and then just like take a thing and let it go. When it gets to the bottom, we'll say it has 0 gravitational potential energy. And again, if you look at gravitational potential energy, kind of like momentum, kind of like kinetic energy, it's all relative. You have to have some reference for what your 0 gravitational potential energy is. Maybe you want to use sea level, maybe you want to use the floor here, or you're using the table. You just need some, it can change. It's all relative. Same thing with momentum, same thing with kinetic energy. And then you add to it 1/2 mv final squared. So what we get from this is that my gravitational potential energy that I start with will turn into the kinetic energy that I end with. And if I solve for my final velocity, I get actually a pretty interesting result. This square root of 2gh has come up every once in a while. Do you guys remember what this comes from? Let's say I had an object, but instead of having it fall on the swing, I let it fall directly down. A straight free fall. If I have a straight free fall, we can use kinematics and try and figure out how it behaves, right? V final squared minus V initial squared equals to 2g, I guess negative g h. Do you guys remember that equation? It was from the V final squared minus V initial squared equals to 2a delta x, that equation. Remember that? That was one of the kinematic equations. If you apply that to a free-falling situation, here's your acceleration, your negative g, your change in position is h, your initial velocity is 0, your final velocity is whatever. Let's see. Oh yeah, I mean, I guess you can say that your h, yeah, well, you're falling, so your delta h is also negative. You cancel out the negative, whatever. Your final velocity is also a square root of 2gh. So that's crazy. Whether you are falling on a swing or you're falling freely, your velocity is the same. This case, the velocity is straight down. This case, the velocity is sideways. How can that? How can they have the same velocity? It is by analyzing it in terms of energy that you can realize there's nowhere else for the energy to go. Because if it's a closed system, you're not transferring energy out. That MGH had to go somewhere. That gravitational potential energy had to go somewhere. This gravitational potential energy has to go somewhere too. Right? And so you get the same result. So actually, as long as gravity is the only force doing work on your system, the motion, the velocities will be the same wherever they fall. One thing I do want to point out, this has two forces acting on it. How come tension doesn't show up in any of the energy? Why didn't tension end up doing any work? Yeah.
Because the tension on the rope is causing it to go in circular motion, and we said earlier that uniform circular motion is a potential force that doesn't go.
Exactly. The motion, the actual velocity of the ball along the way is always perpendicular to the force of tension. Tension is always changing the direction, but not actually in line with the velocity. So your tension doesn't actually do any work. Whereas gravity, it's not perpendicular to the velocity. You have a component of gravity that is in the direction of the motion, which is speeding it up. So gravity is doing work on the ball, but your tension is not. Your tension is always perpendicular to it. Yeah. And so gravity leads to this. So here's the really nice thing. By doing this analysis with gravity, what we're doing is we kind of sneakily calculated all the influence of gravity every step along the way. And with the use of calculus and the math from calculus, it turns out we only really need to know the endpoints. That's what all this helped us do. We didn't have to do all the little steps in between. It turns out we can just figure out what's happening at the ends, which is really nice. It's a very nice tool for calculation. Okay. Questions about this? All right. So that is all gravity. Gravitational potential energy, you need to know that. Deriving this, it can really help to know how to do it. You don't have to memorize it, but you probably really want to know how it works. Okay? You're going to want to know how it works. Later on, when we start getting to more complex, there's only a handful of complex equations where the integrals kind of get dicey. But a lot of the times, I would say, I don't know, 50 to 75% of the calculus that you do for AP Physics C is not harder than this. It's about this level. You're really only integrating or taking derivatives of linear equations, quadratic equations, because that's frankly how most of the fundamental physics in the universe behaves. Newton's second law is linear. Momentum is linear. Kinetic energy, gravitational potential energy, it's all linear and quadratic. So it's pretty straightforward. Okay, the next kind of force that I want to investigate, so we did gravity. The other one is the spring or elastic force. What's that? Someone say something? No. No, we're good? Alright. Period 5. Okay, period 5. Okay, so we haven't really talked about springs or anything so far. Let's kind of talk about some of the basic things about springs. Here is a diagram of a simple spring scenario. Okay, so let's say you have a spring attached to a box on a frictionless surface. Okay, so the spring's going to have a certain amount of length, and usually all springs have some sort of equilibrium position. Okay, so like even if you look at this spring, when I just let it hang with nothing really on it, there's, you know, it has volume, right? It takes up space. From there, if I stretch it, I'll stretch it to some length s. And I'm going to say that this is a positive x direction, is to the right. Okay. So sometimes you have problems where you have to take into account the actual length of the spring. Sometimes you only really care about how much the spring is changing or displacing from its equilibrium. So I'm going to call this distance x. So x is the distance from the equilibrium point, whereas s is measuring from where the spring is attached to the wall or something like that. Okay, so SE is the equilibrium position or equilibrium length. So that x is equal to s minus SE. So for an ideal spring, okay, a spring like this, you look at this, a spring scale. Spring scales or ideal springs behave like this. If I stretch it for a certain distance, it will apply a certain amount of restorative force to go back, 5 newtons to go back. What makes it ideal is that an ideal spring behaves in a proportional, the restorative force is proportional to the stretch. So if I stretch it twice as much, then the force will be twice as much, right? So that for every amount of distance that I stretch, the force goes up by the same amount. Every centimeter, or I mean, it's not exactly a centimeter, it's a little less than a centimeter, but every centimeter essentially adds another 5 newtons of resistance, right? Of restorative force. So, for an ideal spring, we call this Hooke's law. So an ideal spring follows Hooke's law. So that the force from the spring is equal to negative K delta S. Or you can say it's negative K S minus SE. Or you can say negative KX. Any of those expressions pretty much say the same thing. You're just looking at how much extra you're stretching it relative to the equilibrium. So the negative is to take into account that if you have a positive x stretch to the right, the force from the spring should be to the left. It's a restorative force. It should be opposing your changes in stretch. So if you now have x in the negative direction, your force will be in the positive direction. Okay, so positive x, negative f. Negative x, positive f. Something along those lines. Questions about that? So this is the way the force, this kind of force works. If we sum up the forces in the x direction on this box, If it is at a certain position and the only force acting on it is the force from the spring, you'll have a negative kx is equal to an m dv dt. Right? So, I think you can kind of imagine where we're trying to go from here. I noticed that just like with gravity, the force is not a function of time. This force is actually, a function of position, and my work done and my energy tends to be a function of position. I want to see if you guys can try and use the same evaluation method to determine what this potential energy in a spring is. Okay, if you use the same kind of procedure, you should be able to come up with some sort of change in the potential energy of a spring relating to a change in kinetic energy. There should be some expression for this. Just like how there's a potential energy for gravity, which is mgy, and we derive that. I want you guys to try and derive, for this case, what would be the energy or work done by the spring. Okay. So you got, let's take maybe 10 minutes, 9 minutes. Feel free to work with whoever, anyone. If you're in Calc AB, I suggest maybe try working with someone in Calc BC. Try and understand what's going on. But if you're stuck, just look at what we did here. Follow those procedures. But now your force is different. That's it. Give it a shot.
Why is that so funny? You do the same thing as you did. So you split the dv dt, the dv dx and dx dt. So that become dx dt becomes v. So it's mv dv dx, and then you integral both sides and you get that. That was me in calc too. You honestly think you bit your nail.
I've never seen somebody yell at me like that.
I haven't done that. Too much work. My nails get so... Yeah. I can't relate right now. I don't really have... Let's not talk about this. This is horrible. Let's do this. So the 1/2 cancels out. Just hold on to that. What is K? K is a constant. 1/2 mv squared? What was K?
That was just
Yeah, K was 1/2 mv squared. How do you do this, man? Oh.
I don't either, don't worry.
Yeah, but actual.
Straight up from like vegetable, like no, she heard of artichoke. Yeah, that's she heard of vegetable.
okay.
That's because this Gravity. Why did I do that?
Yeah, right, you change and you do that.
Oh. I'm on the right way. Trust me. No, this is fine. You just change in the end. The initials.
Why is it
Why is this M? It's called acceleration. It's M. A is that. So, this is MA, right? A is DVDT.
Yeah.
You change DVDT to DVDX and DXDT, and those two cross out, right? So it's and then so DXDT is just V, right? You change it, so it's just M and add the V here, and that's DVDX. Yeah. My mom's like, why are you so free these days? Like, all of your friends are so busy. I don't know why. They're not doing it. Haven't been. That's the thing. I haven't been. Did they get the video? I have no idea what you did. I feel like they're like, after that, I get what you did though. Or I did something. Yes, she did. I don't know how to change it to K. This is like KX.
The only problem with this is
Oh,
it should be the changes. The changes in them. Right? When we did gravity, it wasn't just MGY, it was the change in MGY.
Oh,
So the same way it's
Integrate it, you have to
you have the initial and final.
just add that part on.
Well, it's important to note that
Like 20 minutes or like
I think you also left out a negative. Oh no. Yeah, you have the negative, so it's the change in
so just put like the line.
yeah.
Hold on.
She was like 20 minutes. But 20 minutes from now, we'll have like 10 minutes. Like pay for it and come on. If it's not exact, then apparently there's like 10 minutes. Right, whatever. Player.
Why is it one?
Mr. Mac, can you check that? It's like just the bottom.
I still can't get over it, but I like it better.
Keep the right side
Yeah.
separate from the left side.
So like,
So
Yeah, that's why I raised the bottom. So like that just changes into JK.
you want to keep the 1/2 on there, so you can keep this as just
And
connected.
then what about the other side?
So the left side,
I'm changing to like 1/4.
no, it was already 1/2, right?
Yeah.
So just go from here. The 1/2 K delta x squared. That's it. From here to here, this is not right. That itself was fine.
So that is equal to.
Your U S. That is your U S.
So it makes so smart.
So here,
Searching for Husserl is hard.
this has an X. It's the same way this has an E.
It's not a.
It'd be like K. So it's actually almost like that.
Okay.
Go now, so you don't ask in the middle of the class.
It's like a teacher. It's like a comedian background, like the used and outliers. Write everything down.
Mr. Wouldn't it be a negative? You having negative changes?
Yes.
Literally, like, this thing takes something else. It takes like 40 minutes to get here. And by the time it gets here,
Why don't we just go downstairs?
She wrote this thesis for us. The problems about water, the struggles of power, and how people relate to the resources.
But they don't know, like, the audience is really, it's a girl, it's clearly a girl, it's like, but there has to be, like, the
Is there Spanish teacher? Oh, CC. I mean, way. Is it way also like? Let's see.
Pizza.
Why are you mad?
Because trying to like, I straight up was like,
Why do I laugh so weird now? It's just you know that makes just made it clear. So it is always the princess. It's always the times have changed. Yeah, actually.
He got to the wrong parking lot, and I went to the left parking lot. I got to the right one.
You need to understand that this should come naturally to you. This should come naturally to you. Joe, have you actually?
Yeah,
No, it's not about. Don't judge that much. They're just like, but like I do judge. So
I can't get any changes. I have to have like 15.
this is why you've been so MIA. Your heart's been flying away, even though your mind's with me. You know what? I don't think
All right, guys, come in and move along. Don't have too much time left, so go ahead, have a seat. Let's go through these steps. So, gentlemen, peoples. So, as we go through the math, okay, the hardest part here is interpreting the math. And that's at the same time the goal. The goal is there is meaning behind this kinetic energy. If I take a spring and I stretch it out and I let it go, it will move towards the center, and then it'll go past the center and slow down, and then it'll move back towards the center and it'll slow down, and it'll keep oscillating, right? There's this idea that there must be a conversion or a transformation that's occurring when it's going fast, as it has kinetic energy, and then when it starts compressing, it's turning it into some other form of energy, whatever the energy in the spring, right? And so what we want to do is we want to quantify that energy in the spring. We know the force provided by the spring, but we want to know, in other words, if I take this spring and I stretch it this far, how much energy is stored in this spring? When I let go, how much energy am I recovering when it flings back? That's what we want to know. We want to compare or find an equivalence between this stretching and its kinetic energy when it jumps back. And that's what this is trying to do. So we use the same trick. We use the chain rule trick. Okay, so I have, and there really is, as we go through these different problems, when you look at Newton's second law, this left-hand side and right-hand side of Newton's second law, F equals ma, is really useful to kind of think of it that way, as there's the left-hand side, which represents all the causes, all the influences, and the right-hand side is the effect, the movement, the outcome. And so when I do this math part, the left-hand side is what's pushing and pulling on it, and the right-hand side I have mv, because this is v, dv dx. And so I'm going to put the dx on the left-hand side so that I look at how the contributions of my spring force over each position causes my changes in my velocity and momentum. Right? So from here, I'll integrate both sides. So originally, the negative kx dx is one instantaneous moment, right? One instantaneous slice of spring force and positional change. What I'm trying to do is I'm trying to add up the net effect of all of those positional changes. Okay, the same way I'm trying to add up the net effect of all these velocity changes. Okay, so I want to point out the similarity in the structure here. You have a variable and the derivative of that, or a differential times the differential variable, right? V dv, and you have x dx. So on the right-hand side, the v dv, this became essentially your change in 1/2 mv squared. Then how about on the left-hand side? It should be very similar. Constant times variable d variable, constant times variable d variable. So on the left-hand side, you should have a negative change in this 1/2 kx squared. Okay. If you're not sure, I mean, in this case, we're kind of using similarity to justify that calculation. But if you want to break it down into the calculus, the actual calculus, k is a constant, so that's negative k integral. You have constant, right? Negative k comes out of the integral x dx. So the question is, the derivative of what function gives you x? And that function would be 1/2 x squared, right? The derivative of 1/2 x squared gives x. But the difference is it's not only the antiderivative. You have to look at it from an initial spot to a final spot. You're adding up a range of little slices, right? And so that's where the 1/2 kx squared is coming from. And this is where it's the change in it. The change is recognizing that it's from some initial to some final spot. And then you can really say kind of the same thing for the other side. M1/2 V squared. V initial to V final, right? So these are really just two different ways of expressing the same thing. You essentially have a change in some expression and a change in some other expression. So if we call K 1/2 mv squared, and we call U sub s 1/2 kx squared, then we can say that the negative change in U sub s equals to the change in K. Okay, so I put the question mark there because I was trying to lead you on to give you an idea of what we're trying to get at. What we're trying to get at is that there's a way of expressing this energy, and that expression is 1/2 kx squared. We're trying to derive this instead of just be given it. This is the mathematical way of determining what that is. Okay. The process of figuring it out is important, especially, that's what distinguishes this class from non-calculus based. The calculus based is showing that you use the calculus to derive all these expressions, all these equations that you would normally see in normal physics or in algebra-based physics. Okay, any questions about this derivation, the steps? The first step is the chain rule part. The rest of it is, I guess you kind of have to know integrals, but I think if you just look at integrals as being this antiderivative method, you kind of already know everything you need to know. It's just the order in which you apply what you know. I guess. Okay, so just like the other one, you'll see that your negative change in gravitational potential energy leads to a change in kinetic energy. In the same way, a negative change in your spring potential energy leads to a change in kinetic energy. So let's look at why that is. As the spring gets pushed out, your 1/2 kx squared goes up. If it moves away from the equilibrium, your spring is stretching out. The force pushes inward. It will slow down the object. As the object gets pushed past the equilibrium point, as the spring starts to get stretched, the stretching of the spring slows down your object. So an increase in potential energy should lead to a decrease in kinetic energy. That's why the negative is there. As this one goes up, the other one goes down. As the spring starts going back towards the center and your stretch or compression is decreasing, you are losing potential energy, and so then it'll start to speed up. It'll start to speed up. And then you gain that kinetic energy back. Okay. Same thing for gravity. Gravity, you lift it up, you lose kinetic energy, you gain potential energy, right? They have that kind of reverse behavior, or opposite behavior. Okay, so in general, these two forces are what we call conservative forces. Okay, it's a conservative force in the sense that the energy that goes into that force, the work done by that force, you can get it back by that same force. Okay, the force gives it back to you. Conservative forces tend to be restorative forces. So you compress the spring stores the energy, and then you let go of the spring gives it back. The same thing with gravity. You lift something up, you store the energy as gravitational potential energy, you let it go, it wants to give it back. Okay. An example of a non-conservative force is like friction. Friction is a non-conservative force. You slide something along, and friction slows it down. It doesn't give it back. It's gone. It's not gone. It transforms it into thermal energy. It transforms it into a different form of energy that doesn't really easily transform backwards. Okay. Whereas again, with the spring, it stays in the spring, and you get it back. With gravity, you store it as gravity. You get it back. Okay. Generally speaking, conservative forces, or forces where the work done is, you get it back, are only functions of position. Okay, so in other words, they're not functions of time. They can't. Well, I take that back. I mean, you could have a force that's a function of time, but I think mainly is you want a force that is a function of position. So friction is not a function of position. Friction is just pushes on you and depends on other things. It depends on how hard they're being squeezed and so on and so forth, and it dissipates the energy. So you look at gravity. These are constant. You look at a spring. This is a function of position. And so you have this potential energy that's like this, and you have this potential energy that's kind of like this. Okay, I don't put the negative in the energy part, even though the negative is in the force, because again, it is also generally speaking true that, well, I won't go as far as to say that, but we can just say that we're just looking at the energy like this. So if your work done is kind of defined this way, then you can kind of see that generally speaking, for these conservative forces, a positive position change leads to a negative force, or something like that. They're, when you talk about potential energy, they tend to be in opposite directions. In other words, you generally don't have a situation where the further something out it is, the harder it gets pushed. It's usually pushing in the other direction. And so you end up getting something like this. Is that generally speaking, then your potential energy change is based on a negative work done, or you can say it the other way around. Okay, this can be super confusing, so I want to make sure I break this down a little bit. Let's look at gravity for a second. When you lift something up, right, it gains position. It gains, if you want to try and push something up, gravity's working against you, right? Gravity's pushing down. The work done by gravity as you lift something up is negative because the work done by gravity is in the opposite direction of where you're trying to move. Okay, so a negative work done leads to gravitational potential energy gain, right? You lift this up, you gain gravitational potential energy, but the force is downward from gravity, so it's working against you. So whenever gravity is whenever you're gaining gravitational potential energy, it must be doing negative work. Gravity's doing negative work. Or conversely, when something is falling, the force is acting in the direction of movement. It's doing positive work, which means that you end up losing gravitational potential energy. And that is generally true for all potential energies, whether it's elastic potential energy or chemical potential energy or whatever, this, spring potential, elastic potential energy, or did I say it already? I don't even remember. Generally, the case of potential energies is that when it adds energy to your system, you are losing potential energy. When it's taking energy out of your system, you are gaining potential energy. Okay? That's essentially what this is trying to say. So we put it all together, you can say something like this. This is really kind of what we're ultimately trying to say. Put it all together. If it is a conservative force, okay, if you have a conservative force, the work done by it is usually a force that is a function of position, which means that you can kind of create this potential energy function. and that potential energy function is usually opposite to the work that's being done. Okay. So this is super confusing as heck. This is why I'm telling you guys, chapter 10 and 11, the math, there's a lot of nuance there, and you kind of have to spend some time like sorting it out in your head and trying to make sure it makes sense. Generally speaking, if you can kind of look at potential energy like, okay, it's storing energy, releasing energy. Where students get really confused or tripped up is, okay, so is it doing positive work? Is it doing negative work? Which direction is the force? Is the force doing positive work, negative work, so on and so forth? So just remember, positive work means that the force is causing it to move in the direction it's actually moving. Negative work means it's trying to keep it from moving in the direction that it's actually moving. Okay? So positive work adds energy to the system. Negative work takes energy out of the system. For a conservative force, the energies that's put in or taken out is related to this kind of stored energy. Okay. We'll get to part 3 on Monday. Try and get to some of the homework problems. I know you get looking at that Thanksgiving weekend like, yeah, I have all this time. Don't put yourself in that situation.